Hello student, welcome to this course PH107 Quantum Physics and Applications. This is the first lecture where I'm going to give a motivation and introduction of this course. Uh, my name is Gopal Dikshit. I'm a faculty member in Department of Physics, IIT Bombay. You may wonder why we need to study quantum physics and applications. Because you may be students in computer science or electrical engineering or mechanical engineering or civil engineering. So why you need to bother about PH107 quantum physics and applications? So let me motivate you why you need to study quantum physics. So before that, for this particular course PH107, we are going to follow Modern Physics by Survey, Moses and Moyer, third edition, which is published in 2015. The front cover of this book looks like this, so you may get one copy of this book, which we are going to follow throughout this course. So why do I learn quantum physics? Quantum physics not only teaches some new concepts of physics, but also teaches us to think beyond our existing knowledge that we are going to see in this course. Moreover, we have to stretch our imagination beyond our current thinking. With these two things in mind, let's go one more thing, that every students and practitioners of science and engineering need it. That I'm going to convince you in this particular lecture. You cannot afford to ignore it in 21st century if you are not going to get acquainted with the quantum physics. It's very difficult to cope up with the upcoming technologies. If you understand it well, you can participate in science and technology that endeavors of 21st century. So let's ask this question from electrical engineering point of view. So suppose you are from electrical engineering BTech student, and where the quantum physics is very useful. So these are few examples where quantum physics plays a very pivotal role. For example, in semiconductor devices, nanoelectronics, where nanometer size quantum tunneling devices are using quantum phenomena. Spintronics, these are the devices which are based on the electron spin. Photonics, these are the devices which are based on the photon. So if you let's say look this USB drive, which most probably you have used to store the data and transfer the data from one computer or laptop to another system. This the working function of this memory device is based on the quantum tunneling, and quantum tunneling is how flash drives erase their memories. This is the hard disk that is present in every computer, which is based on the giant magnetoresistance, which allows us hard disk to function. And this is another example of quantum physics. So this architecture is called quantum wells, which allows you to make, let's say, lasers and photonics. This is a very interesting article written by Kenji Ito from Sokendai University, Japan. And what he writes, from electrical engineering to quantum physics, the case of Nishina Yoshio. And let me quote some of the important paras from this paper. In this paper, I examine connection between electrical engineering and quantum physics research in Japan. Japan was one of the first countries that have successfully developed quantum physics research relatively early outside Europe and North America. Furthermore, he claims that I claim that electrical engineering was one of the basis for quantum physical research to be motivated, legitimized, and sustained. Now, moving from electrical engineering to the computer science, in computer science, one of the current developing and upcoming technology is the quantum computer, and these are two snapshots of the architectures of the quantum computer, where concepts of the quantum physics are used for the building of quantum computers and processing quantum information. The techniques that uses to build these architectures are called low temperature physics, which is cool quantum technology. This dilution refrigerator can cool quantum dots, which are unique architectures or devices, quantum dots, to less than 5 millikelvins for experiment to perform quantum computing. Now, let's move from computer science to mechanical and civil engineering, and this is the picture taken from Caltech, where the quantum mechanics is used at the microscopic level, and this is the picture is taken from a material where the coarse grain density functional theory is used for multi-scale modeling of a material. Now, even if you go to chemistry, where this is a very regular or routine topic in chemistry, where quantum chemistries are taught at the undergrad and postgraduate level, which is a kind of theory that allows us to understand why the bonds are formed, broken, why the chemical reaction is taking place, which chemical reaction is allowed, which chemical reaction is not allowed. And if you go from chemistry to even biology, where quantum effects play a very critical role, and these are the routine textbooks in their respective fields. Now, even the quantum physics is very applicable to finance and market. So these are some of the textbooks that I have taken to illustrate you the power of quantum physics in economics and social sciences. And these are the textbook on quantum economics, quantum social sciences, and so on. So I hope that you agree with me that quantum physics is not only limited to physics, but quantum physics is applicable to science, engineering, as well as to the social science and finance. So what are the uses or where the quantum physics affects your daily life? So here are the few examples which these are different kind of things that you have used or using in day-to-day life, like toaster, fluorescent light, computer, mobile phones. I told you that these based on your silicon chips, biological compass, transistor, laser, microscopy, global positioning system, GPS, magnetic resonance imaging, telecommunication. All these devices, all these instruments, one way or another way, uses the concepts of the quantum physics to function. And this is one of the very interesting article written by Chad Orrell in Forbes, which he explained 3 ways quantum physics affects your daily life. So if you are more interested, you can just Google these keywords, you will get this article. And this is a very, very interesting article which motivates you further why quantum physics is so important. So what are the learning objectives of this course? So quantum physics, or this particular course, is going to give you a flavor of quantum physics in application to solid state physics. And important thing is that this course is going to give some insight on how very well established theories in physics gave way to newer or modern theories. So why quantum physics was needed at first place? So this is a very important question that you may ask, why quantum physics was needed at all. So there were a set of experiments which were not explainable by the existing theory that we call as a wave theory, which we will see it. So theory which questions the wave theory or the wave nature of the light. We will see what is the wave nature of light, or light, which I will show you that light and electromagnetic waves are the same concept. And when these phenomena or these observations made at late 19th and early 20th centuries were not able to explain, or were not explainable by the existing theory which we call as a wave theory, then people started thinking about new theory which we call as a quantum theory. And that's how the birth of the quantum physics came into existence, or quantum mechanics. So let's ask, what is light? So this is Christian Huygens, and he proposed around 17th century that light is wave. And his hypothesis was successful to explain several phenomena of light, for example, reflection, diffraction, and also this theory or wave theory was able to explain the secondary wave fronts, which are a useful concept to explain, let's say, the interference. I will come to this point. On the other hand, there was another hypothesis put forward by Sir Isaac Newton, and he said light, it consists of particles. So he provided that light consists of material corpuscles in motion. So later in late 18th and early 19th century, Thomas Young, which you have seen, showed that the wave nature of light is able to explain the interference from the double slit. That's what we call as a Young double slit experiment. So here the plane wave comes, it passes through the two slits, so you get a secondary wave front, they start interfering, and you see a dark bright fringes on the detector. Now, until this, light and electricity and magnetism was two distinct objects. The unification, or the equivalence between the light and electromagnetic wave, was established by James Maxwell. So what Maxwell did, first of all, he took the concept of the electrostatics and magnetostatics, and he said that first of all, they are not independent, they are dependent with each other. When you say that your electric field is changing with time, as well as magnetic field is changing with time, then the entire thing can be called as electromagnetic wave, and that's what Maxwell set up an equation which we call as a Maxwell equation. And what he showed that the electromagnetic wave is consists of electric field and magnetic field. So if you see this, this is the direction of your propagation, and the electric field is oscillating perpendicular to the direction of motion, as well as magnetic field is oscillating perpendicular to the direction of motion. So electric field, magnetic field, and direction of propagation are mutually orthogonal to each other, and this is the concept of the electromagnetic wave. And when he computed the velocity or the speed of this electromagnetic wave, he found that the speed of electromagnetic wave matches with the speed of light. And that was the first astonishing observation, or the conclusion that made by the Maxwell, that light and electromagnetic wave are the same thing. So here he showed that the speed of your electromagnetic wave is equivalent to the speed of light, which is in terms of the electromagnetic wave speed is 1 over square root of epsilon naught mu naught, where epsilon naught is the permittivity of your free space and mu naught is the permittivity permeability of the free space. So epsilon comes from the electrostatic and mu naught comes from your magnetostatic. So after establishing the fact that light and electromagnetic wave are the same thing, let's move on further. So this is a spectra of your electromagnetic wave, or the spectra of your light, and here you can see that this only a very tiny portion of your electromagnetic spectrum is the visual light, which ranges from 400 to 700 nanometer. And what Maxwell has shown after establishing the fact that light and electromagnetic wave are the same thing, he started performing a set of experiments using electromagnetic wave, and what he showed that electromagnetic wave can be reflected, can be refracted, and diffracted, and they obey the principle of superposition. All these properties were shown by the light. So it means that light and electromagnetic wave are the same thing. With that fact, let's move forward and let's ask one question. This is a question for you to answer. I hope you have seen this laser pointer uh, uh, in different presentations, even in laser shows, even in different movies. Now the question is that what findings of quantum theory are used in realization of laser? How a basic principle of quantum mechanics are used in making lasers? This is a question that you need to answer. So now, uh, by 1900, there was some discoveries which were not explainable or not explained by the classical theory or wave theory. And which are the three? So for that purpose, I'm going to list three examples which you have seen in your 11th and 12th standard. So the first example is the black body radiation. The second is the photoelectric effect, and the third one is the hydrogen spectrum. The black body radiation was first observed in 1860. So these are the times when these phenomena were observed, and these times are when these phenomena were satisfactorily explained using quantum theory. Black body radiation you have learned in your 11th standard, whereas photoelectric effect and hydrogen spectra you have learned in your 12th standard. So what I'm going to do, I'm going to just recap very briefly about all these facts and how quantum theory came to explain all these phenomena successfully. So let me first pick black body radiation. So black body radiation was first observed by Gustav Kirchhoff in 1860, and this is the picture that I have taken from your NCERT textbook of 11th standard, and there is a section 11.9.4 where black body radiation has been discussed. And what you have seen in that section is that this particular curve. What this curve says that along the x-axis the wavelength is plotted or shown, and along the y-axis the radiation energy or the radiation intensity is plotted for three different objects. So the first curve here is the sunlight at a given temperature. This is the temperature at which the radiation is emitted. So this is the temperature of the body which is emitting the radiation. The second one, which has this very interesting curve, is the radiation emitted by the arc at 3000 Kelvin, and this is the radiation at the third one is the radiation coming out from your lamp filament at 2000 Kelvin, and you can see that very small fraction falls in the visible light. So you could see that there are the three different objects which are emitting radiation, and they are behaving at this in this curve in a pretty much similar manner. Furthermore, what you have learned in your textbook, so this is another statement that is taken from your textbook, which is known as a wind displacement law. So if you collect the radiation energy as a function of particular wavelength, and if you see that at what wavelength your radiation energy shows maximum, that is the lambda max, is proportional to 1 over T, or you could say that the product of the maximum wavelength and the temperature is a constant, and this constant is called wind constant. And this observation was very useful, for example, to determine the temperature of those objects where you cannot really measure the temperature physically. For example, a star at in some galaxy from which you can collect the radiation, and you plot the radiation as a function of wavelength and see how the particular radiation is behaving and what value the radiation is showing up the maximum, and by using this expression you can determine the temperature of that particular object. Now this is what we have seen in the last slide. Now after following the Wien's idea, there was another concept that given by the Stefan, and what Stefan has shown that for a body which is perfect radiating, the energy emitted per unit time h is proportional to the fourth power of the absolute temperature of the body. So this is called Stefan Boltzmann law, because Boltzmann provided a tentative explanation or established or helped to establish this expression, and this constant sigma is called Stefan Boltzmann constant, and A is the area of that body which is emitting the this radiation. Now, this is the another part of the book from of your 11th standard textbook, that what the interesting observation that this black body is showing, that the most significant feature of the black body radiation curve, which you have seen in the previous slide, is that they are universal. They depend only on the temperature. That's what we have shown, that you have one curve that is coming out from the sun, the other one is the arc, and the third one from the different filament source. So that depends only on the temperature. All the three curves belong to the different temperature. But these curves or these observations do not depend on the size, shape, or the material of the black body. Now, this is very interesting note that was written. Attempts to explain black body radiation theoretically at the beginning of the 20th century spurred the quantum revolution in physics, as you will learn in the later courses. And when it was meant that you will learn in the later courses, they meant to this particular course where you are going to learn what are the principles behind explaining black body radiation, as well as the principles of the quantum physics, which given a kind of birth to or provided a new seed to the physics. So the first idea or the first attempt to explain the black body radiation came from the Rayleigh jeans around 1900, and what the assumption he made, he said that the sources of the radiation are atoms. So what he said, that you take an object, and when you start heating up, this object is made of atoms. These atoms start oscillating, or these atoms are in a state of oscillation, and these atoms are oscillating like a classical oscillator. That's what you have seen, the displacement of any object from its equilibrium position, and these are oscillating back and forth. And once they are oscillating, they are emitting the radiation. And when he come up with some mathematical formulation, which we will learn at the later part of this course, he tried to fit his mathematical expression to the observed experimental data for a particular object at particular temperature. Here you could see that this data start fitting at a longer wavelength, but as you go to the lower and lower wavelength, or higher and higher in frequency, these Rayleigh jeans explanation, or the Rayleigh jeans expression start deviating significantly. Okay, and it start diverging, it keep increasing, and this is what is technically known as the ultraviolet catastrophe. Now, using this idea, Max Planck come up with a very challenging and I would say a very interesting suggestion or idea. And what he said in 1901, that the elementary oscillators, which Rayleigh jeans said that these are the oscillators. So these are the elementary oscillators which are absorbing the light as well as emitting the light. They can only absorb and emit the light not in a continuous way, but in some units of quanta or some discrete packets. And that's how the concept of the photon put forward, that light is not a continuous wave, but light is also behaving like small units, which you can call as a particles. So light is behaving like a particle, what Newton had proposed few centuries earlier, and these particles are absorbing or emitting lights in certain units. That's what the Max Planck's idea. And then he provided a very detailed mathematical explanation for the black body radiation. And when he put his calculation with the experimental data, you could see that the solid line is the one that is provided by the Max Planck, and the dots are the experimental data, which is shown also here, and they fit very well. At this point, providing the detailed mathematical explanation of the Max Planck theory is not feasible because you require some additional knowledge. For example, how the subatomic particles, electron, proton, neutron, and other particles behave statistically. So you need to know what is so-called statistical quantum physics, which you will learn at the later part of this course. So Max Planck provided a very groundbreaking idea, and he said that the total energy is written in units of this discrete packet, which he called h nu. H later known as a Planck constant, which is of the order of 10 to power minus 34, and n is any integer number, and nu is the frequency of your oscillator. This was the smallest number known at this time. Before that, the only smallest number was known was the mass of the electron, which was around 10 to power minus 31. So this was the smallest quantity that was came by Max Planck, and that's how the quantum physics born. So this simple idea by Max Planck that energy absorbed or emitted only in discrete units or discrete packets was a very bold idea, for which Max Planck received a Nobel Prize, and this is how the quantum mechanics born. So there is a very famous phrase I would like to put forward, that everything begins with an idea, and that was the idea that Max Planck provided. Now let me come to another example that substantiate the power of quantum physics and explain another puzzling observation in late 90s or early 20th century, and that is called photoelectric effect. So photoelectric effect was Heinrich Hertz performed an experiment. The experiment was pretty simple. So there is a metal plate. He shines the light on that one, and when he shines the light, electrons are emitted. These electrons are collected in this another plate, and these electrons are driven along this circuit by the voltage. So the current is produced, and this current is called photocurrent. And if you plot the photocurrent or the kinetic energy of this photocurrent with respect to the frequency, you see a very interesting observation, that you don't see a photocurrent up to a certain frequency of your light, and then after once the threshold is overcome, you start seeing the photocurrent or the kinetic energy of your electron, which is linear with frequency. Another observation that has been seen, that different plates or metallic plates shows the threshold at different frequencies, and that was very puzzling to the physicist, which believed that the wave nature of light is the only existing concept at that time, because according to the wave theory or the old theory, or what people call as a classical theory, that it is the intensity which decides the strength of the current or the kinetic energy of the current, and not the frequency. But the observation shows a completely different way. So that was the failure of the classical theory, that frequency is the crucial quantity, not the intensity of light. And Einstein came and he explained how the photoelectric effect, or how the particle nature of the light is useful to explain the photoelectric effect. So what he did in 1905, he said that, okay, the total kinetic energy of my photoelectrons can be written as the total energy, which is the h nu, which you have seen in the case of black body radiation, minus the work function of this metal plate. And this work function has a certain threshold energy, which I can write down again. This work function is written as h nu naught. So this is the nu naught. And this I have written in terms of the retarded potential. So if I collect these things, I can write down my K max is equal to h times nu minus nu naught. So you can see that your kinetic energy is a linear function of your difference in frequency. That's why you see a linear behavior. And you also see that unless your nu is not greater than nu naught, you are not going to see any current. So you see that using the idea of Max Planck, Einstein borrowed the same idea that your light is consists of particles or photons, and these photons have discrete energy in units of h nu. And by using this concept, Einstein was able to explain uh, um, photoelectric effect, and for which he got the Nobel Prize in 1921. And this is the final simplified conclusion that one could make, uh, is that this is your electromagnetic wave or light. So this is your the direction of propagation. So the light is propagating with the speed of light c, and these are your electric field and these are your magnetic field. That's what we call as a wave nature or the wave theory of your light. And now by seeing the success of particle nature of light to explain the black body radiation as well as the photoelectric effect, now one could see that the light is propagating again along the same direction with the speed c, but in units of photons, which have h nu, or here in picture it's written hf. Okay, so now let me come to the last and the third example where quantum theory was very successful. So this is the atomic spectra of hydrogen. This is the picture taken from your textbook, and here you can see that these are your discrete lines. So these are the lines ranging from deep ultraviolet to the infrared regime, and different lines have different names, depends on who have observed. So these are the Lyman, Balmer, Paschen, and if you go into further details, so you can start seeing this Lyman alpha, beta alpha, Paschen alpha, up to Fund, and so on and so forth. The first question that time was why the lines are discrete, why we are not seeing a continuous spectra. That was a big puzzle around 1880, 1890, and so on. Okay, so the first tentative explanation was given by Johannes Rydberg, and he gave a very hand-waving or empirical formula, and he said that the wavelength of a particular line is related to these two quantities n1 and n2. And what are the n1 and n2? These are the n1 and n2 are your integer number, and he said that there's supposed to be a constant, which we know that this is a Rydberg constant. So once he says that you can choose different values of n1 and n2 as integers, you are able to explain different lines in the spectra. But he was not able to explain why the values of n1 and n2 should be integers only. Okay, it took some time, and then Niels Bohr came into picture, and he provided a successful explanation that why the n1 and n2 supposed to be discrete and what are the meanings of n1 and n2, and he provided the Bohr model of hydrogen atom in 1913, for which he also received a Nobel Prize. So he, by the time when these observations were in the community, and also you have seen that in 1901 and 1905, Max Planck as well as Einstein said that the energy of your radiation or light supposed to be in units of quanta, in discrete quanta. And somehow the same idea or the similar idea Niels Bohr took forward, and he said that not only the light energy can be discretized, but he said the energy within the system or energy of the hydrogen atom are also discrete in nature. That's what the Bohr model said. And these levels have different numbers, and that's how the discreteness comes and explains why the N1 and N2 supposed to be the discrete. So I hope that you have convinced how in early 20th century quantum physics came into existence with different ideas and explained at least three uh, very interesting observations that were not explained by the wave nature of the light, or let's say the classical theory. Uh, Now, before I end this particular lecture, if you would like to read further about these topics, these are the sections where you could read from the same book, Modern Physics by Survey and others. So the black body radiation, you could go to the section 3.2, page 68. Uh, and if you want to know more about black body, as I said, that this is not easy to understand unless you know that it's statistical quantum physics. Then only you will be able to understand the Planck's mathematical explanation. For the photoelectric effect, you may go to the section 3.4 in page 80, and for the Bohr atom, you need to go chapter 4, section 4.3 in page 125. So uh, thank you very much and see you in the next class.